Hello everyone, I'm fortunate to be here to introduce you our mini project. The project name is Closed Simulation based on position-based dynamics. First is project's basic information. Our project is to simulate a closed soft body to interact with their self and static object. Based on Taiji and Open3D tools, we implemented the simulation pipeline from scratch according to the paper by Muller. Our main reference code is for the coarse exercise of the mass spring system. Below are the details about our work. First, let's look at the pipeline difference between mass spring system and position-based dynamics. In the first system, force consists of external forces like gravity, penalty forces from constraints, and collision force from the force-based collision. They will be used for updating the velocity, which may then be updated by impulse-based collision. Finally, velocity will be used for computing positions. In PBD system, however, we only consider external force at first to compute a roughly estimate positions. Since the position may violate internal constraint from material property and external constraint from collision, we utilize projection method to correct estimate positions. Finally, velocity will be revised on projected positions. The key feature of the PBD system is that the constraint can directly change positions rather than apply force or impulse. The paper by Muller further limits the offset direction and the gradient to conserve the object's linear and angular momentum. Constraint has two types. The first type is internal constraint. They could be generated before the simulation. We consider two internal constraints in our work, the distance constraint and the bending constraint. The other constraint type is collision constraint. For colliding with steady object, angle-based broad detection and vertex phase narrow detection is used. The generated constraint is a function of a moving vertex, since the vertices on the steady object could not be moved. For colliding with dynamic object, as in practice, we focus on the self-collision, in which traditional broad detection method does not work, so we skip the broad phase. The generated constraint is a function of four vertices, which means the positions of all vertices will be projected. On the right are the micro demos of two collision types when we are debugging. After position projection, we need to revise the velocity. The revision is generally simple, but for vertices colliding with steady object, the velocities along the surface norm need to be reverted. Friction and restitution are also computed at this step. In our evaluation, we carry out multiple experiments to test the PBT method and implementation. The left video shows the scenario of the close or colliding, which tests internal constraint and the static collision. The right video shows the scenario of close folding, which tests internal constraint and the self-collision. We also carry out basic quantitative experiment to show the effectiveness of ending bending constraint and self-collision. Here are the results. For more demos and comparison under different settings, please watch our full demo video. Besides standard solver, we utilize the differentiability of Taiji to automatically optimize wind force. The loss function is designed to make the close fall on the ball. Despite our best effort, we could only make the simulation until internal constraint projection differentiable. We are still figuring out whether the problems come from the method or the Taiji framework. The right figure is the final result. Finally, for the conclusion, the PBD is an efficient simulation method. It can uniformly represent internal and external constraints, allow users to explicitly control positions. As for drawbacks, PBD is a standard solver. Many parameters still need to be tuned manually. Also, with more constraints added, the whole system is over-constrained. If the projection is not ordered, like parallel computing in Taiji, oscillation will occur. The example below shows fewer oscillation but penetration and no penetration but more oscillations. For our implementation, stability is proved on multiple test cases. Algorithm complexity is acceptable with Taiji framework. 5,000 step simulation takes 147 seconds on CPU and 28 seconds on GPU. However, for higher resolution, border detection must be taken in self-collision to decrease the complexity. The final is our target checklist. That's all, and thanks for your listening.